All right, guys, this video is designed to review the math from test 2B. The majority of you struggled with these problems, so let's walk through how to do all 7 of those so that you'll be able to replicate these on your test corrections. The first 3 problems dealt with the turbines for one city or one town. So for question 1, we were being asked, how many turbines do we need to power a town of 20,000 homes? So here's what we know. We know that one turbine can produce 2.3 megawatts of electricity. We know that each home uses 30 kilowatt hours per day, and that there are 20,000 homes in the area. We also need the conversion rate of 1 megawatt being equal to 1 kilowatt because we have that kilowatt hours here. One thing that we also need to make sure that we know is that we need to convert this into kilowatts. As you'll notice, there's no megawatt per hour, so we have to get rid of that hour somehow. So what we do is we take 30 kilowatt hours per day and we convert it into kilowatts by dividing by 24. Remember, 1 day is equal to 24 hours. So 30 kilowatt hours divided by 24 hours gives us 1.25 kilowatts. This is the piece the majority of you were missing that was giving you such a large number. So we know our need is number of turbines. So how do we solve that? We solve that by taking 2.3 megawatts over 1 turbine, multiplied by 1,000 kilowatts over 1 megawatt, multiplied by 1 home over 1.25 kilowatts. So this way we have everything crossed out except for homes turbines. That gives us 2,300 homes for 1.25 turbines, which tells us that 1 turbine can power 1,840 homes. We take the next step of this, and remember that 1,840 homes over 1 turbine is the same as 1 turbine over 1,840 homes. So we take that, 1,840 homes, we put that with 20,000 homes. Basically what we're doing is we're dividing 20,000 by 1,840. What that gives us is 10.89 turbines. However, we cannot have just 0.89 of a turbine, so we have to round up, which gives us the number of turbines we need as 11 turbines for one city of 20,000 homes. Let's move on to question number 2. Question number 2 was asking us about the amount of money it takes to input these based on the megawatts that are produced. So we know that there are 2.3 megawatts for 1 turbine. There are 11 turbines in the town. 1,000 kilowatts is equal to 1 megawatt, and it's $1,000 per installed kilowatt. What do we need? We need the cost in dollars. So we do 2.3 megawatts over 1 turbine times 1,000 kilowatts over 1 megawatt times 11 turbines over 1. This is just a placeholder. Times 1,000 over 1 kilowatt. The order of these does not matter as long as the placement is correct versus top to bottom and all of those units cross out. What we end up with is $25,300,000 or $25.3 million. You could also have put this in scientific notation and that would have been fine as well. Let's move on to question number 3. Question number 3 was asking us how many turbines would we need to replace a coal-fired power plant that produces 120 megawatts. So again, we have that coal plant producing 120 megawatts, and we also have the 2.3 megawatts per each turbine. So we need to know the number of turbines here. Okay, so how do we solve that? 120 megawatts over 1 coal plant times 1 coal plant over 2.3 megawatts over 1 turbine. We do this because these are reciprocal terms. These are unique and equal terms, sorry. This is telling us this is coming from the coal plant. This is telling us that we're trying to replace the coal plant, so these cross out. What you end up getting is 120 over 2.3, 1 over turbine, because your megawatts will cross out. What this allows you to do is when you have finished solving this problem, you can basically take the reciprocal of this and you get the turbine on the top. When you do this division, what you end up getting is 52.17 turbines. Again, you can't have 0.17 of a turbine, so you have to round up. The answer is 53. That is it for the wind turbine problems. Let's take a look at the next set, which dealt with uranium uses and nuclear power plants. So these sets of problems gave you information about amounts of information, amounts of uranium that are available, the years, length of time the uranium will be used, as well as different kinds of uranium that are yet undiscovered or unattainable. The first question is asking you, how long will undiscovered uranium be able to last us given our current usage? Current usage, the problem tells us, is 70,000 tons per year. My suggestion for these problems is to put everything in scientific notation. So what that gives us is 7 times 10 to the 4 tons of uranium per year. We also know that there are 10.5 million tons of undiscovered uranium. Put in scientific notation, this can be either 10.5 times 10 to the 6 or 1.05 times 10 to the 7. Either of these is okay. I choose to use the 10.5 times 10 to the 6. We need to know time in years. So we take our undiscovered uranium, 10.5 times 10 to the 6th, and we're going to multiply that by 1 year over 7 times 10 to the 4 tons of uranium. The tons of uranium are going to cross out, and we're going to end up with 1.5 times 10 to 2 years, or 150 years. Remember, when you are dividing by numbers that are in scientific notation, you divide the leading numbers first, and then you subtract the bottom exponent from the top exponent. Let's move on to question number 5. Question number 5 asks us how long our resources would last given that we are using better refining. Notice that that better refining reduces the need for resources by 50%. What that tells us is that that resource can last twice as long. From question number 4, we've already determined that undiscovered uranium would last us 150 years at current usage. This is asking us how long in time of years would it last if we were reducing our need by 50%. Simple problem. 150 years times 2, because we're doubling the amount of time we can use it for, gives us 300 years. Let's move on to question number 6. Question number 6 is asking us about usage of uranium extracted from seawater. It tells us that 4.5 billion tons of uranium are currently in seawater. When we put that in scientific notation, that gives us 4.5 times 10 to the 9 tons. From our previous problems, we know that the current usage is 70,000 tons per year, which put in scientific notation is 7 times 10 to the 4. We need time in years. So we take 4.5 times 10 to the 9 tons per year, and we multiply that by 1 over 7 times 10 to the 4th tons. What we end up getting is 0.64286 times 10 to the 5, or 64,286 years. Some of you may get a 5 and some additional numbers. If your rounding answer comes to this, you'll be fine. Now let's take a look at our last problem. Problem number 7 deals with using known reserves and using fast breeder reactors. We know from our previous problems that the current usage is 70,000 tons of uranium per year. Again, 7 times 10 to the 4 tons per year. Known reserves will last 70 years, or 7 times 10 to the 1 years. Fast breeder reactors use only 1% of the current fuel rates. That gives us 700 tons of uranium per year, or 7 times 10 to the 2 tons of uranium per year. How did I solve that? I did a basic proportion. X over 70,000 equals 1 over 100. That's eventually going to get us 70,000 equals 100x. Divide both sides by 1,000, cross out those last 2 zeros, and you get 700 tons per year. And then it's a simple multiplication from there. 7 times 10 to the 4 tons per year over 1, which is a placeholder, times 7.0 times 10 to the 1 years, 1 is a placeholder. This will tell us how long our current reserves will last. The next thing we're going to do is 1 over 7 times 10 to the 2 tons of uranium. What this tells us, this gives us our usage in terms of fast breeder reactors. This is 1% of current fuel use. So we end up with 4.9 times 10 to the 6 years on top and 7 times 10 to the 2 on the bottom. Forgive me, there should not be a unit here. That years should go away. When you divide this out, you end up with 0.7 times 10 to the 4 years, or 70,000 years. One thing to note here, because some of you may be looking at this and seeing 4 plus 1 does not equal 6, this actual multiplication comes out to be 49 times 10 to the 5th years. Just for simplicity's sake, I went ahead and moved that decimal 1 over to make it 4.9. So these are the problems that you covered in your tests. The ones that most people got right were number 3 and number 6. The others were pretty consistently way off. So I hope that this video has helped you kind of figure out, again, how to go through your knows and your needs and to be able to solve these problems accurately with your math skills.